Chapter 13 deals with the properties of gases. Now, I'm sure you remember from early in the semester that matter comes in three physical states: solids, liquids, and gases. Solids are very regular and the molecules or particles are closely packed together. In liquids, the particles are still packed tightly together, but they don't have a very regular arrangement. And in gases, the particles are completely separated from each other. So solids have a fixed shape and volume. If I set a piece of aluminum in a beaker and it's a cube, it's going to remain a cube. Its size will remain the same and its shape will remain the same. With a liquid, the volume is constant. If I take 100 milliliters of water and pour it from a graduated cylinder into a beaker, it'll still have a volume of 100 milliliters, but the shape will be different. In the graduated cylinder, it will be tall and thin, and in the beaker, it's short and wider. Gases, on the other hand, have no fixed shape or volume. So you can put a gas into any container you want, and the gas will simply expand until it fills the entire container. I could take a liter of helium from a balloon and put it in a classroom, and it would spread out to fill the entire classroom. Now, we can describe the behavior of gases with something called kinetic molecular theory of gases, and simply use some basic calculus formulas to describe the various properties of the gases. And right now you're going, oh my God, calculus? Well, of course, this is probably a little bit above Chemistry 3A, so I was just kidding there. Let's take a look at the kinetic molecular theory in simpler terms, something a little more appropriate to Chemistry 3A. So first of all, the terms kinetic simply means moving. So if something is kinetic, it means it's in motion. So the particles of a gas are assumed to always be in motion. At any temperature above absolute zero, the particles of gas will be moving. Molecular simply refers to molecules. Now, gases aren't always made of molecules. Commonly, gases can be molecules or atoms. So if you had a container of carbon dioxide, it would be made of molecules of carbon dioxide. If you had a container of helium, it would be made of atoms of helium. But so molecular simply refers to particles. So it's essentially the moving particle theory of gases. All of the properties or behavior of gases can be reasoned out by simply assuming that gases consist of a whole bunch of particles moving around. So the first point of the kinetic molecular theory is that gas particles are moving at high speeds in straight lines until they collide with something else. If they'll either collide with another gas particle and bounce off, or they could collide with the side of the container that they're stored in. So these gas particles are moving around very rapidly in this container in straight lines. But if a gas particle hits the side of the container, it will rebound off. If the particle hits another gas particle, it will rebound off. It'll still move in a straight line, but in a different direction. The second point of the kinetic molecular theory is very important, and that is that gas particles collide with no loss of energy. They are said to make perfectly elastic collisions. So an elastic collision means that when two objects bounce off of one another, they don't lose any energy. So for example, if we had two molecules of oxygen, each moving 1,000 miles an hour, when they collided with each other, one of the molecules could bounce off moving faster, and one could bounce off moving slower, but in the end, the total amount of energy would be the same. One molecule might leave now at 1,500 miles an hour, and the other would leave at 500 miles an hour, but the total amount of energy would remain constant. In real life, most collisions are inelastic. It's only in atoms and molecules that there are elastic collisions. So let's take a look at an example of a real-life inelastic collision, where a particle will actually lose energy every time it undergoes a collision. Okay, that blue object in my hand is a silicone superball. I learned how to make those when I worked in the chemical industry way back in 1977. They are the best superballs I've ever seen. But no matter how good or how bouncy a ball is, it's never going to be perfectly elastic. A perfectly elastic ball would bounce just as high as where you dropped it, and it would never stop bouncing. And of course, in real life, we know that's not going to be the case. So let's take a look at what happens when we drop this superball. You can see that each time it bounces up, it goes a little bit less. The first time about 39 inches, then 36. Now let's look at a slow motion version of this so you can see a little better. So we'll start at about 39 inches above the ground. First bounce, all the way back to 36, then back up to 33, and finally 29. So the ball bounced pretty well. Okay, that superball is pretty good. It bounces almost 90% of its original drop height. A perfectly elastic collision, that ball would bounce back all the way to 39 inches every time we dropped it. But 36 inches, 33, and 29. So where does the energy go? When the ball hits the ground and bounces up, each time it bounces a little bit less, which means it's losing some of its energy. So initially, the ball has only gravitational potential energy. When I release the ball, it slowly begins to fall and speeds up as it drops, and it's changing its gravitational potential energy into kinetic energy. Now eventually the ball is going to hit the bottom. So if we let the ball go, it's going to drop. And when it hits the ground, it will stop. So when it hits the ground, it no longer has any gravitational potential energy because it's as low as it can get. It also doesn't have any kinetic energy because for that moment when it hits the ground before it bounces back up, it's not moving. So where did the energy go? And the answer is it became elastic potential energy. The ball, when it hit the ground, was squished or flattened, and it caused the molecules in the ball to bend out of shape, and they wanted to snap back into position again. When they snap back, it essentially launches the ball back up in the air again. This time it went up to about 36 inches, maybe 90% or so, and then the ball will continue. Each time it hits the ground, it loses a bit of energy. There's friction. Anytime the ball hits the ground, there's some friction between the ground and the ball that produces some heat. The molecules in the ball rub against each other when it hits the ground and produces some heat. So each time the ball hits, a little bit of its energy is converted into heat, and eventually all of that original gravitational potential energy is gone until the ball simply settles down to the ground. The third part of the kinetic molecular theory has to do with the energy or the speed of the gas molecules or particles. And that simply says that the average kinetic energy of a molecule is directly proportional to its temperature. We learned way back at the beginning of the semester that temperature is a measure of the internal kinetic energy of a material. So the higher the temperature, the faster the particles are moving, and the higher their kinetic energy. So at 25 degrees Celsius, the average oxygen molecule is traveling about 1,000 miles an hour. If we increase the temperature, the molecules will move faster. If we decrease it, they will move slower. It is important to note though that they don't all move at exactly the same speed. It's like traffic on the freeway. Some cars move faster, some move slower. And the same is true with the molecules of oxygen. Some of them might be moving 2,000 miles an hour, maybe some are only moving 500 miles an hour, but the average will be the same. So the average oxygen molecule at room temperature will travel at about 1,000 miles an hour. Now, gases have certain properties. There are 4 basic properties that describe the behavior of gases. The first one of those is pressure. Gases always exert a pressure. As the molecules or atoms of a gas bounce off of the surface, they exert a force against that surface. So that force, when the particles bounce off the surface of a container, say whether it's a balloon or anything that contains a gas, that's what pressure is. Now, pressure has a lot of different units that are commonly used. Most of you are probably quite familiar with PSI, or pounds per square inch. 14.7 pounds per square inch is the average pressure of the Earth's atmosphere at sea level. That means that every square inch of the Earth's surface is feeling a pressure of 14.7 pounds. That's about 15 pounds of pressure. The average person has a surface area of about 4,000 square inches, which means your body is feeling about 60,000 pounds of pressure pushing on it right now. And you might wonder, why in the world doesn't that 60,000 pounds of pressure simply crush you flat? And the answer is very simple. Inside your body, there is the same amount of pressure pushing out. It's the same reason that sometimes when you drive to the mountains or you fly in an airplane, that your ears will hurt. Because there's inside your ear, behind your eardrum, there are air molecules pushing out on your ear. And outside in the atmosphere, there are molecules pushing in on your eardrum. And as long as the number of molecules are equal, it's balanced and you don't notice anything. We only notice pressure when it's different. So if you go up to the mountains and the pressure outside becomes less, there's more pressure inside your ears and it is pushing out and it stretches your eardrums and it makes them hurt. Now, another unit we use for pressure is the millimeter of mercury, and that comes from the device we use to measure pressure, which is called a barometer, invented by Galileo way back about 400 years ago. Essentially, air pressure exerts a force on a substance. So there's mercury in this container, and air molecules are pushing down on the mercury, and they're forcing it up into the tube. Gravity is trying to pull the mercury down the tube. So air pressure can only push the mercury so far up the tube until the force of gravity is simply too great. It turns out that for mercury, air pressure at sea level can raise a column of mercury about 760 millimeters. So 760 millimeters of mercury, that's considered to be normal pressure at sea level. We can also have a similar unit, which is called the torr. Torricelli was a colleague of Galileo that worked on the development of the barometer, and so we often name units after famous scientists. And so the torr is simply short for Torricelli. Either of those units is perfectly fine to use. And a unit we commonly use in gases is the atmosphere. So the pressure of the Earth's atmosphere at sea level is considered to be 1 atmosphere. So each of these 4 units is equal to each other, and therefore you could convert from one to the other. You could set up a conversion that said 14.7 psi over 1 atmosphere, or 760 torr over 1 atmosphere. Any pair of those will make a perfectly good conversion. The second property we use to describe gases is the temperature, or the amount of kinetic energy the gas molecules have. So, as we learned way back in the beginning of the semester, it simply represents the average kinetic energy, or the average internal kinetic energy of the particles. Now, as you're going to find out in the next video, we always measure temperature in kelvins when we're using the gas laws, because kinetic energy is proportional to absolute temperature, which means at 0 Kelvin we would have 0 kinetic energy. Celsius and Fahrenheit are not absolute temperatures, they're relative. 0 Fahrenheit isn't really 0 of anything, and neither is 0 Celsius. So keep that in mind whenever you're working calculation problems with the gas laws. You have to use the Kelvin temperature. The third property is the volume, and that's pretty obvious. Volume is simply the amount of space the gas occupies. And finally, the last property is the quantity, which we use N to represent the quantity because we always measure the quantity of gases in moles. We can't really use an M for the number of moles because we've used M for lots of other things like meter and mass, etc. So P, T, V, and N, those are the 4 properties. They're all we need to describe the physical behavior of gases. In the next video, we're going to be talking about gas laws, the mathematical equations that relate those 4 properties.